Hello friends, today we'll study event trees. Event trees are nothing but it is a technique to determine the probability of certain sequence of event to decide and what improvements are required. Now what are the events? The events are nothing but the events are here we are discussing is uh, accidents or the failure of the equipment. It may be considered as if we take an example of reactor where the exothermic reaction is taking place and we are maintaining the reaction temperature by a coolant by a coil provided in the reactors. So if the coolant is not provided properly, so what will happen, the increase in reaction temperature will take place, and increase in temperature will increase the pressure, and what will happen, there will be a explosion of a there is chance that there will a explosion will take place in the reactor, so due to the increase in pressure. So these are the events, the sequential events that may cause a failure or that may cause an accident to happen. So generally these are, it is nothing but it is called as a runaway reaction. Okay. Now event trees begin, what it does, it begins with an initiating event and work toward the final result. So what we have to do here, we have to find out first what will be the initiation, how the accident will start, what is the initiating event. Now in this example of a reactor, the initiating event is the coolant proper improper flow of a coolant to the reactor. So that is the first event, or it is called as the initiating event of the accident that may cause the increase in temperature. Okay. So that is the initiating event. In this thing we have to find out first the initiating event and we will work towards the final result. So this is the inductive method that provides information how failure can occur and the probability of occurrence. So when an accident occurs in a plant, so what happens generally, various safety systems come into play to prevent that accident from propagating, and these systems either fail or succeeds. Okay. Now if we take an example of same reactor in example of that reactor, so there will be a various safety system will be installed in that reactor. There will be a controllers, there will be a alarm system, there will be a shutdown system, various system will be there. So if the initiation started of the event, so what will happen, it will give some that is a record, it will give some it will give some, so it will give some indications and we will do some work, so to provide that, to prevent that event to happen. So that is the event. The event tree approach includes the effect of an event initiation followed by the impact of a safety system. So what happens here, it will give the idea what what will happen if the initiation of that event started and what are the preventive measures to be done. So that is the event trees. So we will see there are steps involved in the event trees. The first step is to find out or identify the initiating event. Okay. So initiating events will be various types. In the example I have discussed is the reaction. Okay, reactor. So initiating event is the increase in the, the decrease in the flow rate of a coolant, so that may increase the temperature. Now second thing, you have to identify the safety function designed to deal with the initiating event. So there will be various safety measures. So what will happen, we have to find out what are the safety measures that are installed in the that type of example. So reactor, in the reactor, what are the safety functions are designed. So next thing we have to find out, next thing we have to draw the, or we have to construct the inventory, and after constructing that we have to describe the result, describe the resulting accident event and the sequences. So that is the 3 to 4 types of steps involved in that. First we have to find out the initiating event, second we have to find out the we identify the safety function design, then we have to construct event tree. Now from that event tree we have to describe the resulting accident event and the sequences. Now we can say also, we can also do, if the proper data is available, the procedure is used to assign numerical values to various event. So what is that numerical values? There is a failure per year, okay? Then what are the failure rates of each and each equipment that are installed? That is the numerical values. So what are the failure rate, what are the probability, what are the reliability, that we have to find. If the data is available, use that also. Now this is used to find out the sequences and what are the decisions we have to take after the initiating of event is taking place. Now see the example. This is the reactor. We can see the reactor here. There is a coolant is there is a coil is installed in that, and the coolant is continuously flowing through that. The inlet is given, then outlet is given. Okay, the coolant is generally, it is flowing through the coil, and it is maintaining the reaction temperature. Then there is a controller is installed, there is a alarm system is installed, then there is a reactor feed, there is a coolant in, coolant out, a temperature indicator, and the alarm systems are there. So this is a simple example of a system. Now we can see there is a various there is a interactions are involved in that uh, reactor. Okay, so there is a feed, there is a feed inflow, there is a coolant inflow, there is a coolant out, there is a feed, there is a output of that reactor, and again various safety measures or safety functions installed in that reactor. So these are all the that is these things are installed. So here the thermocouple is there, so it can give the idea what are the temperature, what is the temperature of reactor. So this is a simple example of the reactor. Now what will happen here, we have to draw the inventory of this. So that is how to draw it, we will see. Now we can see the consider the chemical reaction system. A high temperature alarm system has been installed to warn the operator of high temperature within the reactor. The event trees, we have to, the event trees for loss of coolant initiating. So what will happen here, we have to first find out the initiating event. Now here initiating event is the loss of coolant. So what will happen if the initiating event is there? What will happen? Increase in temperature will take place, and there will be chances of accident to happen. So this is the example. Now you see there are 4 safety functions are identified in this type of reactor. So first function is high temperature alarm is there, then which will give the temperature is increasing, which will give the alarm. Second thing, second safety function is that operator can noticing high reactor temperature during the inspection. Then third safety function is operating re-stabilizing the coolant flow. Now if the operator notice that the coolant is not working properly, the temperature is increasing, so he will again re-establish the coolant flow. That is the third safety measure. And the final safety is that function is that operator will directly do what he will do, he will directly perform the emergency shutdown of the reactor. So if he notice that temperature has been increased above the certain level, so he will directly he will do the shutdown of the reactor. So this is the 4 safety functions are given during that reactor. Now we see the event tree is written from left to right. Okay, so this is how we can see the example of the event tree. Now we here see there is a left to right, we have to write on the left, and we have to write from the left to right. Okay, now event tree is written in the center of that, and we have to start with that event tree. So this is called as the event tree, where a simple horizontal lines are drawn in the event trees. Now we see event trees are written from left to right. The initiating is written in the first in the center of the page. A line is drawn from the initiating safety event to the first safety function. Now we can see here the initiating is there, so we have to draw the first line. Now first line, what is the first initiating event? That is a loss of cooling. Then how it can take place? Loss of coolant. So first safety function is to write, so we have to write the first safety function, then second, then the last. Okay, that is how we can draw it. Now you see the line is drawn from the initiating to the source safety function. From this point, safety function can either succeed or fail. Now if it is succeeded, it is continuously, we can draw the straight line. If it is not, it is failing, then we have to again draw the horizontal line parallel to that line. Okay. Now you see, by conventional, a successful operation is drawn by a straight line upward and failure is downward, so drawn downward. So this is how we can draw the line. So first thing is the initiating, then the safety function is there. If it is working properly, we will draw like this. If it is not working properly, parallelly we will draw that, and again the last event. So this is how the events are drawn. So that is the initiating first steps that are involved. Now you see, if the safety function does not apply, horizontal line will continue to function. That is how what we have explained. Now for this example, upper branch continues to the second function, where the operator notices high temperature. If high temperature alarm operates properly, the operator will already aware of the high temperature. This sequence description and consequence indicated extreme right to the system. Now we can see by the diagram itself. Now first thing, there is initiating, then what will happen? Operator will notice, again it will, what he will do, they will re-establish the coolant system, and what will happen, there will be a continuous reaction will take place. So there will be no shutdown, there will be directly the reaction, the process is working properly. Now if it fails, we have to again draw the parallel line to that line. Okay, so we see, so that is the first step. The sequence description and the consequences are indicated on the extreme right hand side of the inventory. Now extreme, that is a circle we have to draw on the end of the that line. Now we can see that the open circle indicates safe condition and circle with the cross represent the unsafe condition. So this is how we can draw. Continuous between, that is the same operation, safe operation is carried out, there is no chances of accident to happen. Second thing, shutdown we can take place. If there is a cross, that means there is some problem is there in the plant. Now we see next point, lettering notation is sequences description column is useful to identify the particular event. Now what we have to do, we have to give the letter notation. Now we can see that B is there, C is there, D is there, and E is there. Now what is B indicated? B indicates that high temperature alarm alerts operator. So this is the event. Now you can see here the first notation, it is given to B. What is B? B is the event where high temperature alarm alerts the operator. So C is operator notice high temperature. D is operator restart the cooling system. E is the operator shut down the reactor. So these are the different events that may take place. So that we have to give the notation, letter notation, and A will be always given to the initiating event. So initiating event is nothing but it is given a notation. Starting notation is always given to the initiating event. So we can see the ADE represents here initiating event A followed by failure of safety function D and E. So here we can see ADE is nothing but where is the initiating function first, then second D operator restart the cooling system, and E operator shut down the system. So that is the function that we have to write on the, that is the event trees. Now we see event trees can be used quantitatively if data are available on the failure rates of a function. Now how to calculate the that failure rates? Now if you can see here, these are some points, some numbers are given. So it is nothing but the failure rates: 0.1, 0.25, 0.25, 1. So these are nothing but a quantitatively data for an each event. Now we can see here from the uh, diagram. So for this example, assume that loss of cooling occurs once a year. So let us assume that the hardware function safety function fails 1% of the time are placed in the demand. So this failure rate is 0.01 failure per demand. Also assume that operator will first, that is initiating so operator will notice that high temperature, the high reactor temperature 3 out of 4 times, and that of 3 out of 4 times operator will be successful for re-establishing the coolant flow. So that is a 4 out of, so 4 there is a probability, that is that's why it is called written as a 0.25 failure per demand. So again finally it is estimated that the operator successfully shut down the system 9 out of 10 times. So this failure rate is 0.1 per demand. So how it is calculated we will see. Now we can see here first point. So high temperature, what will happen, he will notice high temperature alerts are operator. So B, for B it is the failure rate of 0.1. So probability is very high, okay, very less. Again operator notices high temperature, so 3 to 4 times. So from that they will have calculated their 0.25. Again operator re-establish the cooling system, again the probability is 0.25. Again operator shut down the system, it is also, it is very 0.15, 0.1. So this is how the quantitative data is written on the system. Then failure rates for the safety function are written below the column headings. Now we can see how the failure rates are written. Now we can see here 0.99. So it is written below the line. Okay, again written below the line. Again written below the line. So failure rates are generally written below the line. Now we can see also next point. The computational sequence performed at each junction, the upper branch by conventional and represent the successful function, and the lower branch represent the failure. So that's we have discussed again also, previously also, that what will happen here if there is a sequence, it is starting from the center and there is a straight line, again it is ending at the, so this is how, this is the safe procedure, okay, there is no, that means the all the safety functions are working properly. So that is the meaning of that sentence. Now the frequency associated with the lower branch is computed by, now what will happen if lower branches are there, so what we have to do, so in that case the frequency associated with the lower branch is computed by multiplying failure rate of the safety function times the frequency of the incoming branches. So frequency associated with the upper branch is computed by subtracting the lower failure rate of the safety function by 1 from 1 and then multiplying the frequency of incoming branch. Now we can see here the net frequency associated with the event is shown in the figure, sum of the frequency of unsafe state. So for this example, if we add all the, for example net frequency estimated 0.025 for failure per year, so that is sum of failure of ADE, ABDE, ABDCED. So that is how these are the function where the safety functions are failing. So we can see here how it is done. So we can see here so all these things are operated and it is added, okay. Now for lower branch we have to calculate like this. So for shutdown it is 0.275 227 2227. So we have to multiply it and we have to write on the line below that. Again for AD is 0.24 runaway reaction where the explosion has been taking place. Then again ABDE, it is this ABD ADE. So again This is how the calculations are done. So how it is done? We have to multiply this by this and we have to find out the value of this. Again, for there will be two consequences. There will be shutdown or there will be shutdown or there will be runaway reaction. So for AD, runaway reaction will take place, accident may happen. So that is the failure per rate. That is how we can calculate it. Now in this event tree analysis shows that a dangerous runaway reaction will occur 0 on an average of 0.025 times per year. So that is once every 40 years. So how we calculated that? Just see then, for runaway reaction, so we have to calculate all these values, 0.24, 0. This, again this, we have to add it and we'll get the value of this. So this is how the 0.025 times per hour per year is the runaway reaction will take place. That means every 4 years the chances of runaway reaction will be there. So from this event we can conclude it. Again we can see runaway reaction. So this is considered too high for this type of installation. The possible solution is to include of the high temperature reactor shutdown system. So what we have to do, we after calculating the value, so we have to give some preventive measures. So here the preventive measures is we have to install the high temperature reactor shutdown. So this, what will happen here? What will happen if high temperature reactor shutdown system is installed? What will happen? This control system will automatically shut down this reactor in the event that the reactor temperature exceeds the fixed value. So emergency shutdown temperature would be higher than the alarm value provided. And so this is how the preventive measures we can give from this event tree. Now we can see also event trees for modified process shown. So additional safety function provides backup in the event that is high temperature alarm fails or the operator fails to notice the high temperature. The runaway reaction is now estimated as to occur 0.00025, that is 400 years once a year. So this is a substantial improvement. So how it is done? So here, from here we can see that the additional shutdown system has been installed. From this diagram we can see additional shutdown system has been installed. So it is added into that reactor, added into that system. So this is how we can give the data. Preventive measures can be included by using that event trees. So that is the use of event trees that we can see. Now here how it is done, we just see that event tree is useful for providing the scenarios of possible failure modes. If quantitative data are available, an estimate can be made of the failure frequency. This is used most successfully to modify design to improve the safety. The difficulty is that most real processes or the method can be extremely detailed, resulting a huge event tree. So there is some advantages, disadvantages also there. If the process is too complex, so there will be a huge event trees, okay, and we have to do more calculations for such system. So that is the disadvantage of that system. So again, event tree begins with the specified failure and terminates with the number of resulting consequences. So if an engineer is concerned about the particular consequences, there is no certainty that the consequences will actually result from the selected failure. So this is the some disadvantages are also there. Now what we can see, what is the major disadvantage we can see here. Now from this diagram, it is a very complex diagram for only a simple system that is given by this event tree for a single reactor only. Okay. Now if we draw event tree for the whole plant, so there is a huge event trees can be drawn and there is a very complex method. So that's why this is the disadvantages of event trees. Again there is a more systems are installed in the plant. So that is a So modified version of event tree is the fault tree. So that we will see in the next video also. So this is all about the event trees are used in the industries. They are generally used to find out the events that may cause accident to the particular area of plant. So thank you.